Before we get started, I have some introductions to do, a little administrative, so I'll get started a little early and then allow as much time as possible for the speakers. There'll be three of them. This is session E9, Design of Frames Using Web-Tapered Members. Three speakers. We'll be starting with Yoon-Duk Kim, graduate student at Georgia Tech, followed by Dick Kaler from Computerized Structural Design, and also Dawn White from Georgia Institute of Technology. Please scan your cards sometime during the session. If you haven't done it already, as you're leaving, please scan your tags for CEUs. Please silent your cell phones so we're not interrupted. And as far as questions go, speakers have indicated that if you have any questions during the presentations, please ask them at that time. So I'll start off with Yoon-Duk Kim. And I'm sorry? Oh, I'm sorry. I misunderstood. Dick Kaler's going to start off. He's on the lead-off circle here.
I'm going to do kind of a what's in the box description of the document itself. We're describing a design guide here. The design guide involved a lot of research and development, but Don and Yoon-Duk are going to pretty much handle the heavy lifting with regards to theoretical and numerical examples. And I'm just going to give you a quick overview of what's in the document, so that you're aware of what's there and whether you'd be interested in when it will apply to your work. Oops. All right, so we have been assigned a design guide number, I'm told, by Cindy Duncan as Design Guide 25. Design Guide 24 is in the printer right now, I'm told, so there's some hope that this document will be released this summer. That's what we've been told anyway. In the meantime, unfortunately, we can't send you draft copies or anything, even though we do get some requests for it from time to time. The reason for the document is that in the last round of the steel specification, it was decided to remove the previous provisions for web-tapered members. Sure. All right. They were developed, I think, around the 8th edition, and but never received widespread use for one reason or another. That was the work of George Lee primarily, and it provided good solutions for particular situations, but the industry had kind of needed something a little more flexible. So they asked Don and I to come up with a whole new approach that would be integrated with the new 2005 spec. And I'm sure all you are working with or struggling with the new 2005 spec, getting up to speed with it. So we had quite a challenge, because usually when we do a design guide, it's a matter of the people who know what's going on just sitting down and writing it down and making some examples and showing you how to do it. In this case, we actually had to do a lot of original research to fill in some gaps. The 2005 specification specifically excluded tapered members at one point. I think it's kind of silent on it now, but there was no thought to supporting tapered members in that document. So we had Don and Yoon-Duk are at Georgia Tech, and about half our budget on this project was devoted to fundamental research into things like lateral torsional buckling of tapered members and shear performance of web-tapered members, things that have gotten some work in the past but needed additional work, and I'll let them tell you about their work. So this document was funded in whole by the Metal Building Manufacturers Association, so you shouldn't be surprised to see that it's somewhat oriented towards their practice. But on the other hand, there's nothing in there that's very particular to them that you can't use. For example, you can learn to design tapered beams, columns, very specifically, and you don't need to be tied into a metal building frame or anything like that. It's quite generic. So we were really writing for them. That industry is heavily computerized. If you go to the exhibits downstairs, now it looks like half of all they sell is software anymore. And the metal building industry has been like that for somewhat longer. So we had to really put together a document that their upper level people could understand and their programmers could understand and really go to town and implement this stuff. So that's what this is. So our goals are stated there. Really, it really had to be a practical document that fit in with the 2005 spec. The document contains some background information, some historical information. Shows some very good detailed example problems on how to design tapered members. Gives you some practical advice on some areas that are helpful, and includes absolutely massive cross-referencing to all previous research in this area. Here's our table of contents. I'm going to stop here. I'm just going to go through section by section. We have a small introduction, and the important thing to most users in here is the scope. The scope was designed around the needs of the metal building people, and all that really means as a practical limitation is there's a maximum taper angle of about 15 degrees that the provisions have been checked for. If you have a more severe taper than that, then you're either extrapolating or you're on your own. The rest of the limitations, the metal building people are much more liberal in how far they'll go than you probably, so you're not going to find the rest of the limitations to be problematic if you're doing conventional type plate girders and things. We have a very exhaustive history of web-tapered member behavior, the work that's been done. It starts with Euler, believe it or not, who actually was the first to look at the problem of a tapered rectangular member, and covers all the work up to present. Very exhaustive. And there's a separate section that explains how our new procedure differs from the older procedure that you'll see in the 8th and 9th editions of the specification. If you happen to be using those, you can see where things have changed. There's a section on design basis, which is sort of a rehash of some of the stuff in Chapter A of the manual, or of the specification. We were working on this document before the 2005 spec was dry on the paper, so we felt we needed to do some education on the new paradigms in the specification, like available strength, required strength, all new terms that hadn't been out there. So there's a discussion of all that in there. There's also an extensive discussion of the provisions of Chapter C, the new stability requirements, which basically boil down to compelling you to use a second-order analysis to design frames and beam columns. And our document is based on the assumption you're going to be doing that. The biggest piece of the document is member design, where we have separate sections on tension, compression, flexure, beam columns, and shear, and a little mention of concentrated forces. Basically, these topics parallel the provisions in the specification. So there's a section on axial tension that looks very much like Chapter D of the 2005 specification. This is not written in specification language. It's written in a little friendlier tone, but it's presented with the same sort of equations laid out in that way. We have a special term that we use quite a bit called gamma E, which is kind of the fundamental thing that we use to pull together the elastic stability of tapered members. And that thing is the factor by which you would multiply the loads in a tapered member to find the elastic buckling state of the member. And it gets used in a lot of the subsequent calculations. With a tapered member, even with a constant force through the member, the stress is always varying. So the way George Lee dealt with it is to say pick an end of the member and look at the stress at that point. We look at gamma E, which is the multiplier of the loads, no matter what kind of pattern they're in, compared with the elastic buckling condition of the member. Don may be getting into it, I don't know. It's something that you're going to use. So there's a section on frame design. This is oriented to a large extent, to some extent, to the metal building people. It discusses some of the issues of modeling with tapered members. There's some interesting things. You get curved neutral axes with unsymmetrical sections that turn up. some discussions of second-order frame analysis issues, some special issues on gabled frames that the metal building people run into. That is a gabled frame with no support at the center where the frame spreads out as it's gravity loaded. It has some little different characteristics, and a very small discussion of serviceability. And then in addition to that big theoretical discussion in the front, there's also an annotated bibliography of an immense number of things connected to stability of tapered and non-tapered members and member strength. There's a set of, at the end of the document, there's a set of appendices that demonstrate some procedures for calculating gamma EL or elastic buckling strengths, in-plane buckling strengths of tapered members. That's one of the big challenges. What's out of plane, basically, it's not such a big problem. In plane, what is the buckling strength of a member that's not prismatic? And then there are some benchmark problems that were put in there largely for computer programmers, but you could use them that show our best idea of some very precise solutions, so that as you're working in this new world of second order analysis, you have some places you can check along the way to make sure your work is matching up with best practice. So I'm just going to give you a couple of highlights on the content. In beam design, we look at one lateral torsional buckling strength per unbraced length. What's new is that we're using the C sub B that comes from AASHTO, basically. And it's the current equation in the specification has a bunch of M's, M at A, M at B, M at C, and M max. The equation we're using is based on stresses, because even with constant moments, the stresses are changing, and that really defines what the moment amplification is. It's the level of stresses, not the actual moments in a non-prismatic member. And Don's research showed that the AASHTO formula was very accurate as the AISC formulation, where the answer was good, and more accurate in the areas where the AISC formulation tails off in accuracy. We basically, out of plane, you can look at the lateral torsional buckling stresses based on the midspan properties. That research kind of comes from Europe and Todd Helweg. And for column design, the big question is, what's the in-plane strength of this member? And basically, our answer is you've got to get an elastic buckling load for that thing and then map that into the inelastic realm, but you can use the specification equations to do that, and Don may be going to show you that. We don't use any K-factors whatsoever in the document. Because we're directly calculating elastic buckling loads of columns, there's no need to get into the whole question of what is K. And the new formulation of the column strength equations, which you see on the right, have you plug in F sub E, which is the elastic buckling stress, instead of KL over R, which was the old way to do that. So that's very helpful for us to have this new formulation available, because we are plugging straight into the AISC equations. We're just getting FE a different way. Method of successive approximations is something we lifted out of Timoshenko from the 20s or 30s, and it provides a way to get a buckling load, in-plane buckling load for a non-prismatic member in a way that's straightforward, and you can program in an Excel spreadsheet, for example, instead of using an eigen solution in some kind of a package. You can go ahead and do this in your spreadsheet, which means you can program it, integrate it into your own software as well, which I've done. Out of plane strength based on the unbraced lengths, based on midspan properties, doesn't vary much. RY is pretty much the same. If you look at the deep end or the narrow end of an unbraced length, it doesn't change much. What's new and interesting in this area is down near the bottom, the thing called constrained axis torsional buckling, the situation that the metal building people have all the time, and you may have, where you've got, let's say, a beam and you've got purlins or joists at 5 foot on center bracing the top flange, but you have kickers or something to the bottom flange at a much larger spacing. So when you're looking at the axial strength of that thing, what's the unbraced length you look at? Is it the 5 feet on the top, or is it 20 feet on the bottom? And the real answer is somewhere in between. And this is something else I think we lifted from Timoshenko. And basically it's a torsional buckling formulation that's based on the assumption that it's buckling about this line of more or less constant braces. And it gives you a pretty good answer, which is somewhere in between. The combined strength equations are right out of the spec, and except for there's a combined tensile and flexural rupture equation, we noticed that the spec didn't really have anything adequate in that area. It's really not appropriate to be taking 8/9 of the moment when you're looking at rupture cases. Those interaction equations are not in any way based on that sort of scenario, so that's pretty much a P over A plus MC over I kind of a interaction equation, and that has now made its way into the current draft of the specification. You'll be seeing that for all members. Nothing interesting about tension. You're just checking local bits and pieces. Some shear work that we borrowed from Falby and Lee, again based on average A over H and H over T values. Detailed example problems on all areas: tension, compression, flexure, shear, and beam column. And that's what I've got. Do you have any questions for me before I turn it over? Okay, thanks.
Okay, so Professor White and myself will present this concepts and calculations based on the new design guide to frame design using Web-Tapered members. And this is the outline of our presentation. We are going to explain the fundamental concept that we used in the design guide and give you the introduction for the example frame that we are going to use to give you an overview of stability analysis and design calculations and summarize the presentation. Okay. So, as Mr. Kaler mentioned, this design guide titled Frame Design Using Web-Tapered Members hopefully will come out in this summer. This guide basically provides extensions to AISC 2005 provisions to allow you to use for the Web-Tapered member designs. So I can summarize the concept in one sentence, which is a mapping of elastic buckling strength of Web-Tapered members to elastic or inelastic buckling strength of equivalent prismatic members. So let's look at this in terms of compressive resistance. So, okay. Sorry. This blue curve is the column design curve we have, AISC 2005. As you see, this is in terms of KL over R value, and we have the limit 4.71 square root of E over Fy to between the inelastic and elastic buckling strength. By the mapping, so by saying mapping, you can map this red curve, which is elastic buckling curve, to the blue curve of the inelastic or elastic buckling strength of equivalent prismatic members. In AISC 2005, there is another term in terms of flange stress, F sub E over Q Fy. And we can have the same limit in terms of this flange stress. This limit becomes 0.44. And this is the formula equation for inelastic buckling strength, and that is for elastic buckling strength. We introduced a new parameter. Here is gamma sub E, which is a multiplier you can use to the F sub R, which is the flange stress under given loading. And by multiplying these two, you can get the elastic flange stress at incipient buckling. So let's say you have these Web-Tapered members, and under a constant axial load P sub R, you will have the maximum value of Fy over Fy value at the bottom, And you can calculate the gamma sub E value by P sub E, which is elastic buckling load over required axial force. An equivalent prismatic member is prismatic member has the same gamma sub E value, and the Fr over Fy value equals to the maximum Fr over Fy value that you get from the taper member. There are several advantages of using gamma sub E parameter with the mapping concept. Designers can estimate an inelastic buckling strength for any type of non-prismatic member and for any member buckling limit state. And also designers can directly account for the general non-prismatic geometries, different angle restraint effects, non-uniform axial forces, and moment gradient effects. So basically, by using the gamma sub E parameter, the overall procedure becomes more general. Okay, now I can introduce the example frame. This is the example frame we selected to show you the overview of this stability analysis design. This is typical modular metal building frame. It's designed by Mr. Dwayne Becker and Chief Industries. This frame has the interior column, which are just simply connected linear columns. It is assumed that for all columns, the base conditions are simply supported, and the yield strength of this frame was 55 KSI. We are going to look at several members. First one is the exterior column member. It's from E1 to E4. Excuse me. This column is double symmetric taper members with the beta taper angle equals 4.37 degrees. It has non-compact flanges, and the web is compact at the bottom and slender at the top. The second member we looked at is this A3-A5 member in the first rafter span. And this is actually a doubly symmetric prismatic member. It has slender web and non-compact flanges. It's in the positive bending. And this is the case where you need to look at the constraint axis torsion or buckling. These marks shows the pulling locations, and these two dashed line indicating that you have the angle or braces from pulling to the bottom flange. But you don't have that bracing for the middle point A4. So you have the embrace length on the outside flange is shorter than the embrace length for the inside flange. We are going to talk about the constraint axis torsion buckling in later slides. The third one is A9, A10, and A10 to B1, which is on the first interior column. Both of them are the single symmetric taper members. A9, A10 has fairly smaller taper angle. A10, B1 has 2.65 degrees. Both of them have slender web and compact bottom flanges, and these are in negative bending. And the last member is in the far inside the rafter span. Again, it is it's prismatic member with single symmetric cross section. It has slender web and compact flanges. This length is in positive bending, and we need to look at the constraint axis torsion or buckling. For stability analysis and design of this frame, we use the AFD load combination, that plus collateral plus uniform snow load case. And we use two pre-approved stability analysis and design methods. First one is the effective length method, and second one is the direct analysis method. And Professor White will talk about the axial resistance calculations.
Okay. All right, thanks, Yunduck. Yunduck and I are going to do a little dance here and share in presenting several different parts of the calculations to you. One thing to highlight in terms of the gamma sub E calculations, it's really the same fundamental concept that George Lee originally used in their good work and that was in the previous specifications. But one way to put it is that where in the previous work the elastic buckling solution was tied into looking at the smallest cross-section on a linearly tapered web, we've generalized that. We have various ways that are provided in the design guide that give you instructions on how to best calculate that buckling value, that elastic buckling value. But the concept of then mapping that to an elastic or inelastic buckling strength is really the same it's the same thing that George was doing in his work. I'd like to present a little on the axial resistance checks to you, and as explained already, we have these 4 different types of limit states that we need to look at in general. A few words about how we do this for the in-plane check for effective length method or for direct analysis method. If we're focused on this particular structure, what Yunduk showed you, it has the exterior tapered columns that are providing your lateral load resistance. All the interior columns are leaning columns. And so all the interior columns, when the frame sways, are tending to destabilize the structure in side sway. In the effective length method, we deal with that by looking at, well, how much can we ramp up any vertical load we have on the system in order to get to a point where we would be at a buckling load in side sway. Okay? The best way to do that, in our view, is to use the story buckling concept that's in the AISC commentary, and it's written in just a generalized form here that gives you the gamma. This comes originally from Lemessurier's work. Again, it's discussed in the commentary, and it's really a part of what you have in the B2 equation. So the buckling load I can get by if I have wind load or some other horizontal load on the system, or if I just put a notional load, some arbitrary lateral load, or an arbitrary lateral load on the system H. I do a first order analysis, I get a delta H. That's the sway of the system under that load. If it's a gabled frame, then we have some discussion about how to deal with the fact that the sways aren't exactly the same because of the opening or closing of the gable bit. The 0.85 plus 0.15 R sub L, that's just a simple accounting for P small delta effects on your large delta drift. Okay? R sub L, if you have a whole lot of leaning column effects, then R sub L goes to 1, 0.85 plus 0.15 R sub L goes to 1, and you essentially have no P small delta effect because everything's coming in from leaning column action. If you have a system where all the load is on the lateral load resisting moment frame members, R sub L goes to 0, you have a 0.85 term there that accounts generally an accurate to a conservative way for the P small delta on large delta. Okay, so that's how we can get our gamma for side sway buckling. If we're doing direct analysis method, then the base calculations in a direct analysis method, K is 1. In other words, we want to look at just a pin-pinned idealization in terms of the end boundary conditions. And Dick came up with a nice formula that gives a very precise fit to the equation that you see down here below. We just do a pi squared EI prime over L squared, where you evaluate your I prime at this particular length along the member, or that fraction of the length along the member. Okay? If we do that for this case, well, you can see here that we get a rather large gamma. We're going to have to get 109 times the design load on this before we could get elastic buckling in this non-sway mode. And that's what the L is actually covering for you in general in direct analysis method. It's making sure that you don't have something in the structure that you've missed that's going to fail in a non-sway mode. Okay. Obviously, we're not anywhere close to that here. Okay, 16.4 is the required axial resistance. So not a lot of axial load in these types of frames, right? Giving us the 109. All right, so now that we've got our gamma, the other part of this mapping that Yunduk had described is we want to look for where's the maximum value of FR to FY, probably at the base here. FR is P over A for the design load that we're checking. Once we have that, we need generally to calculate our Q value if we've got non-slender elements in the column. And so we get an FN, or a column buckling strength in terms of stress, based on that gamma times that maximum FR divided by FY, and assuming Q equals 1. So this is just paralleling the way that we handle that sort of column in the specification for a prismatic member. And then I'll calculate a ratio, we're calling it gamma sub N1 here. It's the ratio of that stress to FR max, at that cross section where you have the hottest cross section. Now, what that allows us to do is to scale up our stress at any location in the column to the level corresponding to that particular stress, the strength based on Q equals 1. We need that to get the F value that we can go in along the column and calculate our Q sub A to get our effective width contribution of the web. We need our Q sub S for the flanges, but that's just working off a flange local buckling check. We combine those together to get QA times QS is Q. We again walk along the column to find where is FR over QFY maximum. And from there, we're ready to do our mapping. We've got gamma, we've got FR over QFY maximum. We can use the column strength equations to get that critical. Then we can do P critical, PR over PC, and then to get our strength ratio. In the direct analysis method, we've provided some recommendations in the design guide that basically allow you to simplify things when you have a case like this one that's clearly not really a stability problem. If alpha divided by your gamma is less than or equal to 0.1, or in other words, if you need to ramp up your buckling loads by greater than or equal to 10 times alpha, where alpha is our 1.6 value, or if you need to ramp up 16 times to get to strength, if it's still not buckled at that level, you basically can calculate your Q based on F equals Fy, get your F critical Q equals QFY. Basically you're working off a cross-section calculation to get your axial strength ratio now. You don't even bother with the length. This is for in-plane buckling. And so for E1 through E4, we satisfy that limit. We go through the calculations. We get F critical 33.4 KSI based on that. Okay, if we bounce over to the rafters for a second, in general for the rafters, in either the ELM or the direct analysis method, we'd get a gamma. There's discussions in the design guide on basically how to go about doing that. I'm going to shortcut that a little bit here. And at locations where our FR over QFY is maximum, again, we would calculate our PR over PC. So it's pretty much the same type of calculations here for that. Let's talk about the out-of-plane strength checks. As Dick mentioned earlier, the common practice is we basically look at each unbraced length as a simply supported segment, K equals 1. The PEY for out-of-plane flexural buckling, it's for all practical purposes prismatic in that direction anyway. And we just use the IY at the middle to do that calculation. Torsional buckling, we provided some recommendations that I think are very useful to keep you out of having to get bogged down in the mud with torsional buckling or torsional flexural buckling cases. If you have a doubly symmetric member, and if KZL, so everybody know what KZL is? Probably not. The KZL is basically typically taken as the length between where you're preventing twists, right? And so if KZL is less than or equal to your KYL, because usually that's the case, Basically, we did some studies to show that torsional buckling isn't necessary to be checked at all for a doubly symmetric section. You'll never have an error there that's significant in neglecting the torsional buckling in those cases. If KZL is bigger, then you've got to worry about it. For singly symmetric members, now we have to deal with torsional flexural buckling. If KZL is less than or equal to KYL, and if the cross sections either are such that if you have equal width flanges, and if the ratio of your thicknesses is between 2/3 and 3/2, then you're good to go to calculate your gamma just based on out-of-plane flexural buckling. You don't have to go to the more involved torsional flexural buckling equations to get your elastic gamma. If you don't satisfy these, then you need to go do the torsional flexural buckling calculations. All right, constrained axis torsional buckling. I think Dick already described this well. I was thinking of maybe, we call it cat buckling, so I was going to draw a little picture of a kitty cat, and with his hair standing on his back or something like that. But anyway, I'll spare you the humor. The typical cases here, the length between the points where we're restraining out-of-plane movement on the inside flange larger than the outside flange. And so if we look at the PEY, basically based on the inside flange brace spacing and outside, the constrained axis torsional buckling will fall in between those two. And so we have this situation on the rafters here in this particular example. We calculate that strength using the cross-section at the mid-span of that length that you're checking. And now Yunduk's going to walk through the flexural resistance.
Okay, so for flexural resistances, in general we look at the flange local buckling, tension flange yielding, and lateral torsional buckling. We include the AIC yielding limit state for the flexural resistances. For flange local buckling and tension flange yielding, these checks are basically the cross-section checks. So even with the taper member, you can use the AIC 2005 provisions directly. And you can check those at several locations within that embrace length, within your member, and you can find the largest value of flexural resistance check as the governing check for the member. And the checking for the tension flange yielding is not necessary for the doubly symmetric segments and segments with the larger tension flange, which is exterior column and A3A5 and C5, C7 member in this example frame. For lateral torsional buckling, we have to look at the similar fundamental concepts similar to the ones used in the column strength calculation, because the lateral torsional buckling involves with the boundary condition and the applied loading. And so we determine the elastic LTB stress for the uniform flange stress case for the given Web-Tapered members. We suggest to use the alpha B is the embrace length of the compression flange, and you have to use the J equals 0 if the member has a slender web anywhere within an embrace length that you are looking at. And we suggested to use the Ashto 2007 equation to calculate C sub B, which is this equation, and please note that this equation is in terms of flange stress. These are the illustration how you can calculate the C sub B with this equation. So when, for example, in the segment E2, E3 in the exterior column, this is basically the flange stress diagram for a given deload case we were looking at. And this blue curve is the original flange stress diagram. And based on the Ashto equations, you get the F1 over F2 ratio values equals 0.85, which give us the C sub B factor equals 1.07. And so once you get the F sub E LTB and C sub B values, you can plug those into the nominal LTB strength equation in AISC 2005. In the design guide, we expressed that same equation in terms of flange stress. And one more recommendation we have in the design guide is that when you determine the R sub PG factor, instead of using Fy, you can use the M sub n based on the RPG equal 1 over the section modulus. By using this term, you will get a little more liberal value for the R sub PG factor. And we recommend to calculate the M sub R over MC ratio at both ends of the taper members and at the midspan and the location where you have the maximum value for FR over Fy ratio. For this particular case, this location is at the deep end of the taper member. Okay, so we are going to talk about combined resistance check.
Okay. All right, last dance. Okay, so I'll describe how we put this together in terms of the beam column checks. Equations H1-1 are applicable. We could talk for a while about why they are, but we won't. We'll determine the governing axial and flexural strength ratios for each segment of the member, and the unity check here label as UC. That's just the particular one that we're going to be hitting here, and often we'll hit. We're in a low axial load range, and so we're just focusing on this particular form. There is the other form of the beam column interaction equation that applies if you have higher axial load. Okay, so let's suppose we're going to do the beam column check for one of our exterior columns here. And so now what you have to get your head around is, let's see, if I'm dealing with in-plane buckling, it's the whole thing E1 to E4 that I'm working with and thinking about, well, it's going inside sway. Okay? And so if we look at the numbers we get based on what I had described earlier, when we walk through the calculations for this, we get 0.161 for that. We would, for out of plane, we would go and separately check E1, E2, E2, E3, E3, E4. I'll just show one example. Let's suppose we're just interested in what's going on in terms of checking E2, E3. So this check for E1 to E4 applies to E2, E3, okay, for in plane. For out of plane, I focus on just that length from E2 to E3. And I got 0.182 for the axial ratio there. And so 0.182 is larger than 0.161, and so that one controls. That's the one you see highlighted here in the table summarizing our results. By the way, we don't have copies of these here, but if anyone wants to leave us your cards, I think we'll be happy to send you a PDF of the presentation. All right, so there we were, 0.161 in plane for E1 to E4, 0.182 out of plane if we were checking that. You know, the E1, E2 was actually the governing one of all those segments, but again, it's non-prismatic, so it's not like checking a prismatic column necessarily. We need to look at each one. Okay. The flexural strength ratios, let's say we're using the direct analysis method. Flange local buckling check governed here. The flange local buckling check works essentially, you can think of it as a cross-section by cross-section check. It was 0.663. We got 0.590 for lateral torsional buckling check on that particular segment. And since that was a longer segment, that one actually did have a larger, oh wait a minute, no, it's flange local buckling. I'm getting confused. Okay. All right. Okay. So if we're focusing on segment E2, E3 as an example here, we put these together, get our unity check, we got 0.75. For the value, it's less than 1, so this segment is okay. Now, to compare a few different numbers out of the different calculations we can get, if we look at that particular segment, and if we consider the effective length method that's boxed in gold there, what actually happens here is when you do the proper effective length method calculations, this frame has a lot of leaning columns in it. And you got to knock down your P sub C to deal with that leaning column effect because you're not dealing with it on the moment side. In the direct analysis method, you're getting amplified moments that handle that part of the design. So you design with PC based on k equals 1 or base k equals 0. I showed you an example here. Okay. With the direct analysis method, since we're really nowhere close to being a stability issue here in this case, when we're looking at a non-sway failure, 0.182. We put everything together. We get from the effective length method a unity check of 1.1. So that violates the requirements somewhat versus the 0.75 that I showed you. In a typical design calculation using prior or working off of the prior AISC 1989, we get 0.68. That was with a typical approach of saying, oh, K is 1.5, and we keep moving along. Doesn't matter how many leaning columns you put in there, K is 1.5. Okay. If we look at the rafters, our axial strength ratio there, pretty much the same, either effective length method or direct analysis method. It's because both are pretty much non-sway checks there. We put that together with the moment ratios. We get essentially the same answer. It's a little bit, just a shade higher in direct analysis method. Why? Okay, we're paying a little bit of penalty there because we're saying, wait a minute, we've actually got imperfections in the frame. We need to deal with the uncertainty and stiffness. And when we deal with that in the direct analysis method, we get slightly higher moments. So that tends to penalize us a little bit in many cases in the rafters. A 0.01 penalty here. If we look at the typical unity check from prior type calculations, 0.76. Okay? All right, so to summarize, the new design guide, when it is here, is more general and we think is going to be easier to program, easier to use than the previous provisions. The direct analysis provides definite advantages when you get into cases that are non-rectangular type geometries like gabled frames and so forth. So I think it's very useful application of the direct analysis method here. In fact, if you have something like the modular frame that we're showing you here, because it's so wide, you've got a lot of gravity load that's beating up the frame there with all those leaning columns on the interior. And so, at least in some of your gravity load combinations, it's not uncommon with a frame like that to get side sway amplification that's larger than the 1.5 limit, where you're no longer allowed to use the effective length method. The direct analysis method provides substantial savings relative to the effective length method if the calculations of the stability effects are all done on level playing field. And the design checks from the direct analysis method and the effective length method are practically the same if you're looking at the rafters, but fairly common that you may see a little bit higher strength ratios in the rafters with the direct analysis method. And lastly, I believe, the new design guide will, in some of these cases, provide slightly higher unity checks. That's pretty much what I just said in respect to the rafters. So that's it. Again, we'll be happy to provide handouts by email if you would like some. And also, as a little advertisement, two of my colleagues, Stan Lindsay and David Wright, and myself, we're working on some online courses. We dig deeper into some of these things. And they start May 1st. I put some sheets in the back, if you're interested, on the table that give a little bit of a description of that. Thank you. Oh, right there.
There was a comment made that these design guidelines were based on work done up to 15 degrees taper.
Yes.
If we go back, take a slide back to slide number 7.
Okay. Let's see.
It had a graphic about axial loading.
Mm-hmm.
It looks to me like on the tapered side, that axial load is actually parallel to the vertical flange and not.
Mm-hmm.
So you're defining axial load as being parallel to one flange?
Oh no. The axial load is the load that would be tangent to your centroidal axis.
Okay. And this analysis also takes into effect on the fact that neither flange then is parallel to the neutral axis.
That's correct.
Okay.
That's correct. And the method of successive approximations, or many of you may know it better as Newmark's method, works very well for that. It basically allows you to get upper bounds and lower bounds, and the way that we're posing it for doing the calculations. In many situations, you don't really need to iterate. You can iterate and get improved results, but Dick, I guess most of the times just a single cycle, and we were in pretty good shape, right?
Yeah, word is great.
Yes.
What are the experimental results that can back up everything that you presented?
Mm-hmm. I'm going to let my PhD student handle that question.
First of all, we don't have much of the... Oh, sorry.
Okay.
Okay. First of all, we don't have much data for the experimental tests reserved for the taper members, but
more than we did in 1970.
we did find some of the experimental data by the Pryor et al. And some Xiaomi and Krata and some of the paper that has a few of the taper member test data. But those are mostly in compact sections. So it's not really directly compared to what we usually have with the standard web. But we did compare those with the final element analysis.
Yeah, basically, we looked at every experimental test we could get our hands on. There's not a whole lot. And Yundok and I live in an area called finite element land, and we do a lot of numerical simulations with geometric and material nonlinearity, distributed plasticity, residual stresses, geometric imperfections, all in there. And we could talk about that longer, but you probably don't want to hear it. Yes, sir.
Let's look at the column sections E1 through 4.
Okay.
And some will ask, what about unity checks at points in between E1, E2, E2, E3? Should that be a concern?
The E1, E2, E3, and E4 are just the points where we have the ends of the member where it's framing into the panel zone or the column base, or where we have the girts. We probably glossed over that a bit. Generally, you would check, help me here with, we have some recommendations so that you don't like check 1,000 points along the member. You check the location where FRFY or QFY is maximum. Okay? You typically would check, I think we would see some cases where we get a maximum where your case of C value in the buckling check might transition out, get down to 0.35 and then it holds constant at 0.35. So the cross section where you hit that, all these things are varying along the length of the column,
So
right?
there is some criteria.
Yeah. So you're not just checking at the ends. That's correct.
There's only a few places that can govern and you've identified.
Yeah.
Okay. One other question. Both the European code and the China code have specific criteria for web-tapered members. Did you look at that? Was it of any value?
Yes and yes. I think what we have here is I think it's fair. I think it's fair to say that a lot of the prior work has gotten lost in the forest because of all the trees. And I think we have an approach here by focusing on the gamma and say, gosh, we got to get an elastic buckling load for the different limit states that we're checking. And now let's look at where the stresses are hottest in the member. And if you put those together, one thing I'll often get, or will often get questioned on is, wait a minute, isn't that going to be a little bit conservative? Yeah, you could probably tune it a bit and argue that we're erring a little on the conservative side there. But in terms of the checks to experiment or checks to refine finite element analysis results for the strengths, I don't think you can. I think it falls out of the statistics in looking at what you get there.
How does this fit with seismic requirements?
We'll let my esteemed practicing co-author answer that question.
Well, these are, in the metal building world, these are R=3 type seismic design category, B and C type frames. I don't think there's any reason why if you were working with seismic with compact members, any of this wouldn't work. Because it really is just extension of the existing strength provisions with some corrections to the elastic buckling strengths that are then mapped into the inelastic strength the same way that prismatic member is. It wouldn't worry me if you were using seismic with compact members. It just wouldn't worry me that it would be a problem. So you have proper welding details and all the things you would need if you were fabricating prismatic shape.
Professor Cheming Wang is doing work at University of San Diego. He's made a good argument that for a lot of these types of frames, essentially an elastic seismic approach is probably justified. But if you get things like heavy hard walls, tilt-up walls in there, things like that, then you can't get it to work that way. So then, as far as from the research side, I think the jury is still out on how to best improve on those things. Yes, sir.
Is anything, most of these sections are just welded on one side, so you only have a weld on one side. When you looked at the actual equations for lateral and unsupported members, they're actually, because of the web is giving the support, often, as a matter of fact, you'll actually have a tilt on the flange, and the tolerance for tilt is quite large.
Right.
So the section usually requires the IASC specification for lateral and unsupported.
Yeah, that's a good question. Professor Ura did some tests at UT Austin and they were one-side welded. They weren't tapered though. They did them as a prismatic test. I think you gain some benefit in terms of the residual stress Also, the Falvey, not Falvey, the test by Professor Lee student that we used. Prowell and Lee and others. Yeah.
I forgot the second name.
Yeah. Sorry. Those members were also one side welded, and there's some residual stress information that was published there, and it referenced a report, and Professor Lee apologized, but he couldn't find the referenced report. He did some looking for me to try to locate that.
You're indicating that there's actually an increase in resistance?
Increase because you got to help from the residual stress. Now, I think what you're asking about is, do you get distortion from the welding and some imperfections that may push you the other way?
It's usually the NVMA has much larger tolerances for
Yes.
imperfection than the ILC does.
Yes.
AWS are built up numbers.
Do you recall what imperfection amplitudes we're using in our research?
It was L over 1,000. We used imperfection magnitude of L over 1,000,
With the
L
local
being
bucket.
field baseline.
For distortion, local distortions, things of that sort?
Yeah.
Yeah, okay.
That's less
All
than
right.
NVMA.
Yeah. But UNDOC hasn't finished her doctoral thesis yet. So. That's an excellent topic.
Bad question.
Okay, it's going
Right.
to 7 years.
Right.
8 years.
This gentleman here had a question, he put his hand up before, I'm not sure if he's glad to talk. Any other questions? If not, this completes the presentation.
Thank you.